Hello student, to wave optics course. Today we have lecture number 31 where we will discuss more about the Huygen's theory. So, we have lecture number 31. So, in the last class we discussed the Huygen's theory, which suggests if we have a wavefront that is moving, each point of the wavefront, for example, this is a wavefront, a part of the wavefront will going to produce secondary source, spherical source, and then the tangent of these things will going to propagate. So, for a propagating wave, this is the wavefront and each point on the wavefront is a secondary source. It also produces these kind of spherical wavefronts, and if I join the tangent line, then that should be the next wavefront and so on. So, this is the way in Huygen's principle the light is propagate, the light will going to propagate. And now, in today's class what we try to understand that this is the direction of the propagation, and if it is at delta t time, then if the velocity is v, and then v multiplied by delta t with this distance, and this is the direction of the light propagation. So, if light is propagate in a particular direction, then the corresponding wavefront what we draw is this dotted line, and you can see that this dotted line, that is the wavefront of this propagating light. Assuming that the source is present at infinite, then this wavefront is basically perpendicular to the direction of the light. So, this is the wavefront, and this is the light ray. It starts with a point, even though this is start with a point, and this is the way the wavefronts will going to emerge or propagate. And when it goes to a very large distance, it essentially look like a straight wavefront. So, initially it is circular, and then for a sufficient length, after propagating a sufficient length, sufficient distance, this is the form of the wavefront one can have. This is called the plane wavefront. So, we have a plane wavefront for a large distance. So, assuming the light is coming from a source which is placed very large distance, then this is the way the wavefront will going to move, and that should be perpendicular to the light rays. Now, let us try to understand the laws of reflection and refraction in terms of these Huygen's theory. So, that should be one of the today's topic, and so laws of reflection from the wave theory. So, already we introduced wave theory through this Huygen's theory, that light is propagating in a particular direction, and then this wavefront, on all the points on the wavefront are the secondary source of the secondary sources, etc. So, based on that, first we try to understand the laws of reflection. So, let us draw this. So, this is the interface or the reflecting surface, and so the light ray will fall here. These are the 3 light rays that is falling over the surface, and let me draw the corresponding wavefront here, which should be, maybe I can put a different color. So, this blue line is the corresponding wavefront, and the light rays are this that is falling on the surface. If there is no such boundary, then light should propagate, and this wavefront should move without any obstacle. And let me draw a wavefront here, and the light ray is essentially reached to this point, and this point. Okay. So, let me now put some names here. Suppose this point is A, this is A1, this point is a B, this is B1, and this point is C. Also, there will be, because of the presence of this AC plane, which is a boundary and through which the light is reflecting back, then what happened that the ray that is coming through A, in absence of this boundary, it should go from A to A prime, but because of that there will be a reflection of light. So, let me draw this reflected light here, and this is the reflected light for first ray. So, this is ray, this is let us put O, this is the reflected light for O, and this is the second ray, and third ray that is hitting it C. Now, according to this Huygen's theory, what happened that there will be a secondary wavelet, and if I join the this curvature, the tangent of this curvature, so that should be the wavefront of this reflected ray, which is again perpendicular. So, let me draw it carefully. So, that dotted line that I put here is the line that is joining this envelope that is created by this reflected ray, and that should be the wavefront of this reflected ray. So, now let us put let us designate the names. So, this is A, B, this is A1, B1, C, and no, let us put this as B, this point as B, the wavefront, let us put the name, and this point as C, and this point is C1. I should not write this as B. This is B. This is B1. So this B should not be there. Instead of that, let us put a different name, D. And the reflected ray that is hitting here is A2, and this is B2. Okay, so that is the structure we have, and this angle, so this angle whatever I am drawing here is the incident angle A, incident angle, and this angle OAK or angle A is designated by I. This angle, however, that is making the reflected ray, I call it R. Okay. Now, let us start. So this incident wavefront I defined as ABC, this line, and the reflected wavefront I defined as A2, B2 and C1. This is the reflected wavefront. If the light velocity is V0, so V0 is the velocity of light, then A, if you note carefully, A1, that is the length the light should propagate in absence of any boundary at some time t, will be V0 t. But because of the presence of this boundary AC1, the light reaches from A to A2. So, A2 is equal to V0 t as well. So, essentially we have A2 will be equal to A1. That is the condition we have first. Now, let us consider these triangles. There are many triangles that is formed here. So, let us consider one by one. So, from triangle A2 and C1 and A1 C1, these two, that is A2 C1 and A1 C1, what we get, you can see that the angle A2 C1 is 90 degree. So, let me write it here, angle A2 C1 is equal to 90 degree, and A1 C1 is also 90 degree, and they have a common line AC1 and also AA2 and AA1, they are same. So, these two triangles are similar triangles. On the other hand, another triangle is there. These are similar. In the same way, we have DB2C1, and so this and this, they are identical triangles, and also from triangle A2 C1, this is, and D B2 C1, they are similar angles, and from that these two and A1 and triangle D B1 C1, these two triangles are similar. These two are similar triangle. Since these two are similar triangle, then we are allowed to write A2 divided by AC1 is equal to this, and this ratio is D B2 divided by D C1. This is one equation, and another equation also I write A1 divided by A C1, that is equal to D B1 divided by D C1. This is equation 2. So, from equation 1 and 2, and to go to next page, as A2 is A1, so we can have B D B2 is equal to D B1. What is the meaning of that? The meaning is, if I look, so D B2 is equal to D B1, that is D B1 is this, D B1 is this, and D B2 is this. So, they are same. That is when the ray is reflected from A to A2, during this time B will reach D and then reflect it and go to the point B2. Exactly here it should reach. The geometry suggests that it should reach exactly at this point over this line. Once this is ensured, then the rest part is straightforward, and let me write it here. That angle, as I mentioned already, angle A2 C1, which is equal to angle A A1 C1 both are 90 degree. So, let me check which angle I am talking about. So, A2 C1. So, this angle I am talking about, this angle and this angle, they are 90 degree to each other, and if that is the case, then I can write that A2 AC, which I defined as R, and A1 AC1, this angle is also R. Okay. So, these two angle should be R. So, I have angle A2 A C1 is equal to angle A1 A C1, this is R, and also one important expression I have, that's I plus R is 90 degree. So, if I go back and check it, that this is 90 degree, this angle is R, and this, if this is R, then this angle, let me draw it, then this angle must be R. So, you can see that I plus R should be perpendicular, because K A is perpendicular to the plane of this reflection. So, this angle R and I, they are I and R, if I add these two, they should be 90 degree. So, if that is the case, then we can have OAK and also this angle KA. So, yeah, so let me check here. If that is the case, then I already have the, so angle OAK then has to be equal to angle KAA2. Which angle I am talking about? Let me go back. OAK means OAK, that is, this angle is nothing but I, as per we define, and that is equivalent to KAA2. And what is KAA2? KAA2 is basically the reflected angle. So, that is nothing but the reflected angle. So, this angle is same. So, I should have this as I. So, that means incident angle is equal to reflected angle. And that is the law of reflection. So, exploiting the Huygen's theory, that how the light will propagate in terms of these wavefronts, one can show that the laws of reflection basically holds. So, this is one law. So, another law I need to prove quickly, and that is the laws of refraction. From the wave theory. From the exploiting the wave theory, we will do that. So, again let me draw, this is the interface I am drawing, and I draw This is the perpendicular I draw, and then light will fall here as before. Three rays will fall here. And let me draw the wavefront the way we did earlier. Which is perpendicular to the ray. This is the wavefront I am drawing. And if this interface is not there, then the light should reach somewhere here. Somewhere here. Okay. And the light I draw is this. Here, this point, but the refractive index here in the upper and lower region is not same. So, here the velocity of the light say v1 and the refractive index is n1. This region the velocity is v2 and the refractive index is n2. Since there is a change in the refractive index and velocity, so the light will move in a different direction, and suppose it goes in this direction after refraction. This moves in this direction, and this is the wavelets that is generated. And if I draw the tangent, then that is the So, this line is basically the tangent of these things. Okay, I need to erase a bit. Yeah, this. Now, I define, say this is the ray O hitting the point at A, and this is A, say M N. This is the wavefront that is moving, this point and this point, and the rays are coming this direction, and then it moves to here and here. This point say B, and this point is C. So, this is A1, this is say B1, this point is B2, and this point is A2. Okay, this is the way the light is moving here. And say this point is K. K1, and this is K, say. So, what is the incident angle? Let us define this first. The incident angle here is this I. This is the incident angle, and this angle is the refracted angle R. Okay. So, now let us start with our treatment. So, here N1 with the refractive index which is C divided by V1, and N2 should be C divided by V2. So, AA1 will be V2 multiplied by T. This is the time taken the light to go to AA1, but if there is no boundary, then the light should go A to A1, A to A to A2. So, A2 will be V1 into T, that is the light propagating in the original medium, that is N1. So, from again from triangle A1 C and triangle B1 C, which are similar triangle that we already described in the last calculation, I can have important expression like A1 divided by AC is equal to B1 divided by BC, and also from triangle A2 C and triangle B2 C, in a similar way we can write A2 divided by AC is equal to B2 divided by BC. Just taking these two angles like before, I can have two important expressions, and these expressions are, one is this and another is this. Now, once we have this, then the rest of the part is straightforward. Here I should put that few information, that angle A1 A C A1 A C, that angle is 90 degree minus R, right. Similarly, angle A1 C, which is 90 degree, A1 C, this is 90 degree. So, if that is the case, then I can have, so angle A C A1 AC A1, that is I am talking about this angle, that should be equal to R, and that is equal to B angle BC B1. Okay. Now, also in the same way, I need to go to next page. Also in the same way, angle A2 AC, that is 90 degree minus I, and angle A2 C is 90 degree. That means, I am talking about this angle A2 AC, this angle. So, A2 C is 90 degree. So, this is 90 degree, this angle is 90 degree, and then A2 AC, this is this 90 degree minus this. So, this is I, because this angle is I, this entire angle is I. So, so I have this is 90 degree. So, A C A2 is I, which is equal to angle B C B2. So, from that we find an interesting thing, that this angle ACA2, that is I am talking about this angle is I. This small one is R and this big one is I. So, once we have this, then rest of the things are simpler. So, A1, which we already got, AC, that is B1 divided by BC, is nothing but sine of R from simple triangle BCB1. Similarly, A2 divided by AC is B2 by BC. It should be sine of I from triangle BCB2. So, if I combine these two, A1 divided by A2, it should be sine R by sine I, and that is V2 divided by V1, and that is N1 divided by N2. So, we have N1 sin I is equal to N2 sin R. This is nothing but the Snell's law or law of refraction. Okay, so I don't have much time today to discuss more about Huygen's theory, but mostly we try to show that using the Huygen's principle we can find out the general law of reflection and refraction. Further, in the next class I try to introduce two different kind of diffraction phenomena. One is called the Fraunhofer diffraction and another is called the Fresnel's kind of diffraction phenomena. In Fraunhofer kind of diffraction phenomena, light will go from infinite and the source point is infinite, and also the screen will be placed at the infinite. But in the Fresnel case, light is a finite distance and so as the source. And then in two cases how the diffraction pattern will going to differ, and different conditions and different aperture. If I put different aperture or different disturbance to the light wave, then what kind of pattern as a diffraction phenomena one can obtain in the screen we are going to discuss. So, with that note I would like to conclude here. Thank you very much for your attention. See you in the next class.